Alright, in today's video, I want to talk about basic circuit analysis and the 4 things you need to know to solve almost any circuit. I'll explain how resistors work in series and how they work in parallel. I'll also give an explanation of Ohm's law as well as Kirchhoff's laws. Resistors in series can be reduced by just adding them together. Because they share the same wire, the current through them is always going to be the same, but there are voltage drops across each resistor. So resistors in parallel are slightly different. We need to keep in mind that the voltage at each of these nodes is going to be the same, but because each resistor is on a separate wire, the current will split into different paths. If you wanted to reduce the resistors in parallel to only one resistor, the formula above gives us a way to represent the equivalent resistance. Alright, now we have Ohm's law. Ohm's law states that V is equal to IR. Kirchhoff's laws are also very important. We first have KVL, which is Kirchhoff's voltage law, and then we have KCL, which is Kirchhoff's current law. Alright, let's first take a look at Kirchhoff's voltage law. This fundamental law states that the algebraic sum of all voltages around any closed loop in a circuit is equal to 0. I'm going to show a quick example around a small closed loop just so this makes sense. Let's say we have a 10-volt battery. How can I determine the voltage with reference to 0 volts at these other points around my loop? Using Ohm's law, we can find the current in order to determine the voltage drop across each resistor. We can add up our series resistors and manipulate our equation to solve for the current, which happens to be 33.3 milliamps around this loop. We can then multiply each resistor by our current to determine the voltage drop. After some simple math, it's time to verify our solution. If we have 3 equal resistors, it makes sense that the voltage drop across each resistor is the same. Taking a look at our loop, we start first at 10 volts. Then after that, we drop 3.3 volts. We then drop 3.3 volts once again, and then another 3.3 volts before we get to the very end. If we take a look at KVL, the sum of all voltages should be equal to 0. 10 volts minus 3.3 rep of 10 times 3 is equal to 0, so our math checks out. Moving on to KCL, Kirchhoff's current law states that the algebraic sum of currents entering and leaving a node or junction in an electrical circuit is equal to 0. Let's picture 2 wires with our junction in red. We have current coming in from the left side, and that current must split between 2 different paths. Now taking a look at these different currents, let's label our currents here, I1, I2, and I3. So KCL states that our split currents, I2 and I3, are going to be equal to I1. Now is the moment you've all been waiting for. We are now going to take a look at an example using all 4 basic principles. Starting with a more complicated resistor network, we can use what we know about resistors in series and parallel in order to simplify our circuit. We want to break our circuit down to only one loop, so we can use Ohm's law to get our starting current. I'm doing the breakdown here pretty quickly, but I'm essentially just breaking down the resistors into more manageable components so we can solve our circuit. Alright, getting to our final breakdown, R2 and R5 are in parallel, which means we can combine them. Now we can find our resistance equivalent. We can use Ohm's law to find our current, which happens to be 5 amps in this case. But once we expand our circuit back out, how will we find the voltage drop across different resistors in our circuit? We can find the V drop of R1 using the current we solved for. We can't solve R2 this way because the current has split, but taking what we know about KCL, we can see that the current I1 is the same current going through our bottom resistor. We can use our solved current to find V drop of R3. Now, knowing our voltages across R1 and R3 allows us to make an algebraic equation to solve for R2. This gives us a 30-volt drop across R2. We can also verify our answer using a current division equation. This allows us to solve for the current in the R2 branch, and we can see that 3 amps times 10 ohms gives us 30 volts. So now that we know these voltages, how can we solve for the voltage drop of R4 and R6? Well, we can solve for the current I2 by dividing our voltage by our resistance at that spot. We can then use what we know about KCL to solve for I3. In order for KCL to be true, I3 must be 2 amps. Now that we know the current I3, we can just multiply it by our resistance to get our voltage drops. I want you to also notice that if we add up all the voltages around the outside loop, our KVL equation still holds. This allows you to check your answer and verify that each voltage drop solved for is correct. Expanding our circuit once again, we can take a look at the closed loop in the box and solve for the one unknown voltage. After some algebra, we get a drop of 8 volts. So now if we expand our circuit once again, we can see that R5 and R10 are in parallel. This means that the voltage at the two upper nodes should be the same and we don't have to do any math. Now we finally made it to the final expansion of our circuit. Using KVL, we know that the voltage drops across these resistors must add to 8 volts. We can compute the amount of each drop using a voltage division formula that basically gives us a voltage based on a ratio of resistor values, and this helps us solve our circuit. Alright, that's the end of the video, guys. Thank you so much for watching once again. I hope you enjoyed this video, and I hope you also learned a lot about basic circuit analysis. These principles are fundamental for any electrical engineer. If you want to see more videos just like this, like and subscribe.